Welcome everyone. My name is Goel. I am a postdoctoral researcher at ETH Zurich. In this presentation, I will talk about our IJCAI 2020 paper, Peer Prediction in the Presence of Outcome-Dependent Lying Incentives. This is joint work with Aris, Filos, Ratsikas and Professor Faltings. So this paper is motivated from the observation that in many real-world scenarios, information collected from agents is used to make a decision or determine some form of outcome. And agents in these cases often have external incentives to manipulate the decision or outcome by misreporting the information. So let me give a motivational example for this problem. And this is really just an example. The problem is more general. So consider the case of service level agreements for web services. Usually when we sign up for a web service, the service provider promises us a certain quality of the service. For example, the response time will be less than 2 seconds. If the service provider violates this agreement, we are entitled to get some compensation. Now the question here is how to decide whether the service provider violated the agreement or not. The traditional way to do it is to bring in a trusted third party who monitors the service and reports whether a violation occurred. However, there are multiple issues with this approach. First, third party is costly and it must be trusted by all other parties involved for this approach to work. And also the traditional solution is a centralized solution that may not be acceptable in a world that is moving towards decentralization. So what is the alternative? A fundamentally different system would be to not use any trusted agent and ask the users directly whether an SLA violation occurred in their case or not. This kind of approach will give rise to what we call as decentralized oracles. And this is not a new concept that we are introducing in this paper. In fact, two of the largest ICOs running on Ethereum blockchain for prediction market also propose to use a similar concept of decentralized oracles in future. We actually have another paper at IJCAI 2020 explaining more how a decentralized oracle can be implemented in Ethereum. Unfortunately, it's much more challenging to make this kind of system work in practice. Why? The main reason is that users have incentives to not tell the truth. In our web services example, the users clearly have an incentive to report that the response time was low to receive the monetary compensation stated in the SLA. So the research question before us is whether it's even possible to get truthful information from the agents in a financially profitable manner when there are outcome-dependent lying incentives. Let me make this setting a bit more formal. Let's look at one of the questions for which we want to collect information. Let this question be called Q, which asks whether the response time of service X was less than 2 seconds or not. Multiple agents submit answers for the question. Let's assume that for this question 47 people say yes, the service was good, and 3 people say no, the service was bad. Once we have collected the answers, we aggregate them into a single outcome for each question. One way to do it is to just keep the fraction of people giving a particular answer as the outcome. For example, what fraction of people reported a bad service? So in our example, 3 out of 50 people reported the service as bad, so the outcome is 3 by 50. Now, based on the outcome determined, people get some monetary benefits. For example, in the case of web services, this monetary benefit comes in the form of a refund. In our model, this refund is equal to a fraction of the maximum possible refund K, and that fraction is equal to the fraction of people who reported the web service to be bad. So for the example that I just gave, the refund becomes K times 3 by 50. In the previous slide, we just saw one way to calculate refund, but the refund model is incomplete without specifying who is entitled to get the refund. One possibility is that we give that refund amount to everyone, irrespective of whether someone reported the service to be good or bad. We call this refund model as the generous refund model. Alternatively, we can have a more conservative refund model in which the refund is not issued to everyone, but only to those who complained, meaning only those who reported the service to be bad. Now, clearly, in any of these two models, reporting bad service is the dominant strategy for every agent. So what does that mean? Well, it means that truthful feedback elicitation, which is already a very hard problem, becomes even harder when such outside lying incentives are present. We show in the paper that it is possible to build not only truthful but also financially profitable decentralized oracles even in such difficult and impossible looking settings. In the rest of the paper, I will focus mostly on the generous refund model, but the results can also be extended to conservative refund model. So how do we do that? We do that by implementing a side payment scheme to incentivize truth telling. Peer prediction or peer consistency mechanisms are game theoretical mechanisms that incentivize self-interested rational agents to report truthful information. The attractive feature of these mechanisms is that they don't require any ground truth for verification of the information provided. They have been shown to elicit effort and truthful information from agents, but no one has analyzed what happens when there are outcome-dependent lying incentives for the agents to lie. Do the mechanisms still work? A state-of-the-art peer consistency mechanism is the peer truth serum mechanism. We will be focusing on analyzing this mechanism in particular in the presence of outcome-dependent lying incentives. So how does this mechanism work? So suppose that an agent submitted an answer Y for a given question, and then there is another agent, we call this agent as the random peer, who submitted the answer Y dash for the same question. So the payment rule for PTS is we reward the agent according to the formula 1 minus P upon P if the answer given by the agent and the random peer match, where P is the relative frequency of the answer Y in the answers collected for statistically similar questions. And if the answers do not match, then we charge the agent 1 unit. Now, to deal with lying incentives, what we propose is to simply scale the payments with a positive scaling constant alpha. So we pay the agents alpha into 1 minus P upon P if the answers match, and otherwise we charge alpha. So once we implement this mechanism in our settings, we get a couple of very interesting and desired results. Before introducing the results, let me just go through some notations that I will use to present the results. I will use K to denote the maximum refund that any agent can get. That is, it's the refund when every agent reports the service to be bad, or in other words, when the outcome is 1. I will use N to denote the total number of agents who submit answer to a given question. And finally, I will use delta to denote an estimate of the self-predictor value. So what is self-predictor value? Intuitively, it's the correlation strength between an agent's and her peer's observation. For an example, you can think of this as a quantity whose value is higher when the agents believe that the quality of service is more homogeneous. The mechanism does not know the precise value of self-predictor value but has an imperfect estimate of it. So the first theorem that we have is that given delta, which is an estimate of the self-predictor value, and a sufficiently big scaling constant, the truth-telling strategy profile is a strict equilibrium if we underestimate delta and is an approximate equilibrium if delta is overestimated. So now that we have made truth-telling an equilibrium with sufficiently big scaling constant, the next obvious question is this approach profitable in the sense that do we have to pay a lot of money to get trust from the agents? To concretely answer this question, we introduce a metric that we call as the relative saving made by the side payment scheme. This gives us a way to quantify the financial profitability of this approach. It is defined as follows. Here, NK is the total refund when no side payment scheme is implemented. Why? Because when no side payment scheme is implemented, the rational outcome would be 1 because every agent would report the service to be bad, and since there are n agents, we would end up paying NK as total refund. P is the total side payment plus total refund when we do implement PTSC mechanism to get truth from agents. And we can compare the relative saving of our mechanism with the maximum possible relative saving. The maximum possible relative saving happens in the case if the agents somehow magically become honest and they tell the truth even if we don't implement any side payment scheme. Of course, this is hypothetical because the agents are rational, but this gives us the value of the maximum possible relative saving, which no other solution can exceed. Note that the upper bound on the relative saving is the probability of a good observation and not 1. This is because there will always be some refund that we will have to make even if everybody is truthful. And that refund gets smaller, or in other words, the relative savings get bigger if the service is good. So we have the following theorem providing a lower bound on the relative saving that we can make with the PTSC mechanism. The interesting points to note here are that number one, the relative saving is always positive given a sufficiently large number of agents, and it approaches the optimal relative saving value as the number of agents tends to infinity. With PTSC mechanism implemented, the denial strategy, that is the strategy of always reporting a bad service, is no longer the dominant strategy but is still an equilibrium. We show in the paper that it is possible to eliminate this equilibrium if the agents believe that there exists a non-zero positive fraction of agents who would answer honestly. We also have several numerical experiments to show the utility of our approach in the real world. We used a publicly available dataset of real-world quality of service evaluation results from 339 trusted agents on 5,825 web services. In this dataset, the agents observed the response time in seconds and throughput in kbps of the web services. We discretized the dataset to binary signal space, the details of which are in the paper. So here are some of the results. Let's just focus on the graph on the left hand side. The top line that you see in the graph is the optimal relative saving, and it does not depend on n. If you remember, it was just the probability of the service being good, so it remains constant as n grows. Then you should see the orange line just below it. It shows how relative saving quickly approaches optimality in the truthful equilibrium as n increases. The rest of the two lines show the change in relative savings with number of agents if some of the agents do not play the truthful strategy, despite the PTSC mechanism. This may happen if the mechanism's estimate of their self-predictor value is not good enough, or if some of the agents don't behave rationally, for example. Even in these cases, as we can see, we can make significant relative savings. So to summarize, in this paper we considered the settings where agents have external incentives to manipulate a decision or outcome that is determined from an aggregate of the information reported by them. We saw that a peer prediction mechanism, in particular the PTSC mechanism with the derived scaling constant, guarantees that truth telling is an equilibrium and the undesired equilibria is eliminated. We further showed that the lower bound on the relative savings in the net payments achieved by the mechanism approaches the optimal value with increasing number of agents. I encourage you to read the full paper, which is available on my website, and I look forward to your questions and comments during the live session or through email. Thank you.